Should see a little red flashing dot in the upper left-hand corner of our Zoom windows. So we are recording, and now I will hand it over to you guys.
Thank you, Dr. Trom. And we are ready. Okay. Hi, we are group 4. My name is Zachariah Benuna.
I'm Nicola Woodward.
My name is Cindy Long.
I'm Rachel Pleites.
I'm Kate Gonzalez.
I'm Daniel Espinosa.
I'm Adam Ellenbogen.
I'm Sagar Das.
And I'm Guillermo Aceves.
And this is our product, the Vitatron. Vita, stemming from Latin roots meaning life, and Tron, bearing its origins in Old Norse, meaning to grow and thrive. Vita Tron, where your cells will live their lives, grow and thrive in our autonomous microbioreactor. Now, the Vitatron was separated into 6 separate subsystems. The liquid handling, sporting a 3-directional gantry system capable of adding and subtracting liquid from all wells and test tubes. The gas control, capable of putting in 5 different compositions of gas within the chamber. The ODFI, which ensures monitoring of all the cell culture with optical density and fluorescent intensity measurements. The housing, with 3 layers of insulation, a compact footprint, and 3 rows of LED lights attached to the roof to ensure photosynthesis needs are met. The heating and cooling, capable of reaching any of the desired temperature while doing so in less than 15 minutes. And lastly, the agitator, with 3 different shake patterns and boasting a wide range of RPM.
So each subsystem was assigned a technical readiness level. At the first slice of each subsystem, you will see a figure which will represent the technical readiness level. A red figure means a technical readiness level of 1, which means the basic principles have been observed and reported. An orange figure represents a technical readiness level 2, which means the concept and or application has been formulated. And a yellow figure represents a technical readiness level 3, which means that the concepts have been demonstrated analytically or experimentally. So for the housing, it's a 3-layer composite wall. The innermost layer is made out of polypropylene sheet that is 1/8 of an inch thick. The middle layer is made out of a polystyrene foam that is 1 inch thick. And the outermost layer is made out of 34 stainless steel sheet metal that is 0.048 inch thick. In addition, we also included a door that is 24 inches wide with 22 inches tall that will allow the customer to reach all the parts of the bioreactor. Around the door, there's going to be a seal to ensure that no air will exit or enter the bioreactor through the door. And to lock the door, we included an electromagnetic lock. Next to the housing, we included the electronic and equipment compartment, also called the EEC. As you can see, the EEC has an emergency stop button that when pressed, it will cut power to all the bioreactor. And in order to return power to the bioreactor, you will need to twist the red knob to reset it. Also, we included a 20x4 LCD display. But 20x4 means that there are 4 lines, and each line is able to hold 20 characters. On the EEC, you can also see their indicator lights, which they can indicate normal operation, a warning light, or a danger light. And to wrap the EEC, we include a USB port. The USB port will allow a computer to connect to the bioreactor and communicate to the bioreactor and get all the data that the bioreactor is collecting.
Okay. And in terms of other functional benefits of our housing, we have its compact design when compared to our competition. Coming out to just 42 by 36 by 25 inches, it comfortably sits on your average lab benchtop. And then each layer's material was chosen to optimize insulating power and cost, while also taking into account other material properties that worked in our favor. The innermost layer, made of polypropylene plastic, is a non-reactive material, which is important because this material will be the closest in contact with the cultures and also needs to properly contain the specific gas and temperature conditions within the chamber. Polypropylene was chosen for having the lowest thermal diffusivity out of other contending materials for the interior of the housing. The middle layer is a polystyrene foam, more commonly known as styrofoam. It helped provide a high enough thermal resistance to keep the outside of the housing from getting too hot, because calculations showed that just the polypropylene and the stainless steel layers didn't provide enough insulation. Polystyrene foam was chosen for its highest insulating value for its cost when compared to other insulating materials. And then the outermost layer was chosen to be 304 stainless steel for its non-corrosive and high strength properties, which were our greatest concerns for the exterior, without resorting to more expensive metal alternatives that would provide similar material properties. And because this was modeled after a small household mini fridge, something every college student is familiar with, it's worth mentioning the insulating properties of the walls. The thermal resistance of the combined 3 layers ensures the exterior remains at a temperature safe to touch to any operator around the bioreactor. And not only that, but the insulation helps prevent energy waste by the bioreactor. The insulating power retains at minimum about 90% of the heat consumed by the heating and cooling system, making sure temperature control remains efficient and power is not wasted, saving the user operating costs in the long run.
Given the 5 gases specified by the customer, nitrogen, hydrogen, methane, carbon dioxide, and oxygen, we performed calculations using the specific heat and density for each gas at room temperature, the highest hot temperature, so 70 degrees Celsius, and the lowest cold temperature, 4 degrees Celsius. Doing this, we found that the biggest change between 70 degrees Celsius and 4 degrees Celsius would require around 700 kilojoules per second heat rate for hydrogen. Therefore, given the time constraint that we were given of 15 minutes, we reversed this to find what would be the minimum power required by the heater and the chiller in order to achieve this temperature change. Using the NTU method, which uses the heat exchanger performance, we found that 88.25% of the heat rate going in through the chiller is effective, or like shown in the heat sink. Therefore, we found that the maximum energy needed to produce by the chiller was around 1,000 watts. As you can see here, the chiller produces 1.52 watts, or kilowatts, the one that we found, and the electric heater produces 1.17 kilowatts. So therefore, these temperature changes would comfortably be done within 15 minutes.
To begin discussion on the gas control subsystem of the Vidatron, I asked to direct your attention to the 5 nozzle inlets that reside within the mounted aluminum box for gas control. Each pipe is connected to one of the 5 gas reservoirs, one being for oxygen, one being for carbon dioxide, one being for methane, one being for nitrogen, and one being for oxygen, nitrogen, methane, carbon dioxide. Yeah, I got them all. Okay. The gas control flow rate is regulated by solenoid valves that are connected to each pipe. And each of the solenoid valves are connected to an Arduino on the floor to control them. As seen in the top left of the chamber, there is a pressure relief valve installed, which will operate in tandem with the gas control valves, essentially allowing for excess gas to be removed. As long as there's a way for gas to exit as gas is coming in, we can avoid the system from becoming pressurized. Now, in the instance of failure of the pressure relief valve, we have also installed a pressure transducer that resides within the control box, and that will give an internal reading within the chamber to give an advanced warning to any experimenters if there will be an increase in pressure and the system starts to become pressurized. Now, to give a reading on gas composition, an array of gas sensors from the company Grove is installed within the chamber, each one specifically calibrated to detect a specific type of gas. From top to bottom, we have hydrogen, methane, oxygen, carbon dioxide, and for nitrogen readings, we are going to do subtractive calculations. Lastly, the HEPA filter is installed. It is within the chamber, and it will help prevent airborne contamination. The reason we chose the HEPA filter was essentially, as you will see, the gas control valves will pass air through the said HEPA filter, and the two fans from the heating and cooling subsystem, one being on the heat exchanger, one being on the electric heater, will create airflow within the Vitatron, essentially meaning that whenever any air gets in, such as when you open the door to the Vitatron, the airflow within the chamber will pass the air particles into the HEPA filter, therefore keeping everything clean and avoiding airborne contamination.
In going into more detail about the airborne contamination control within the chamber, the HEPA filter was installed specifically to meet our BSL-2 safety requirements. And as Adam mentioned, the filter was placed adjacent to the fans integrated into the heating cooling system to encourage airflow through the filter. Taking into account the power rating of the fans given by the manufacturer and the pressure drop across the HEPA filter, the time estimated for an air change within the chamber is about 0.98 seconds, assuming ideal conditions. This should be sufficient to keep the airborne contaminants from reaching the cultures.
Moving on to our next subsystem, we have the liquid handling system. Our liquid handling system is split up into two parts. We have our gantry system and then our liquid dispensing system below. Now, as far as our gantry system goes, during our design phase, we decided to take inspiration from certain competitors, such as various companies that do 3D printers, laser etching machines, and other competitors such as Opentron, that also make bioreactors. And we decided to base our system on simple components that could be managed with low cost and could be assembled with ease. So with our gantry system, we decided to choose ball screws. Ball screws will enable us to achieve X, Y, and Z movement in all three directions as required by the customer. We have chosen NEMA 17 stepper motors, 4 of them. 2 of them will be driving ball screws in the X direction, 1 in the Y direction, and 1 for the up and down Z direction. These NEMA 17 motors were chosen because they're relatively low cost, and they will be able to meet the needs to provide the torque needed to move the weight of the entire gantry system. Our system was calculated to have a speed of approximately 275 millimeters per second, which will enable plenty of time for our gantry system to be able to move and pinpoint cell cultures to add or dispense fluid. And we were able to achieve a precision of about 0.025 millimeters to pinpoint exact locations on where the system needs to be. And below our gantry system, we have decided to outsource our liquid dispensing system, once again from Opentron. We have their single channel P1000 Gen 2 syringe, which will enable us to hit a volume of about approximately 100 to 1,000 microliters with an accuracy between 2 to 7 microliters. And then additionally, we have a scaled up Opentron that is mounted on the other side of it. This is similar to the P1000, the only difference being that it will be able to achieve a higher volume of approximately 1,000 to 10,000 microliters with just a slight decrease in accuracy, but it will still be able to meet the needs of the customer to pinpoint and extract more liquid as needed. So continue with the liquid handling system, just to give a more detailed information about it. Like I said, we're using 4 NEMA 17 stepper motors. They utilize a step angle of 1.8 degrees per revolution. And they also have a maximum speed of 4,600 RPM. And by analyzing the torque curve of the motors, we determined that the optimum RPM in order to ensure the motor will be able to provide enough torque to handle the load was 3,200 RPM. So that was made within spec of our machine. As I stated before, our XYZ movement speed linearly is going to be 275 millimeters per second, which was found by using various equations, getting the screw lead, getting the screw pitch diameter, using Pythagorean theorem to get the helix length per screw revolution, multiplying that by the RPM of our motor at 3,200 RPM, we get our speed of 275 millimeters per second. And then also to get our minimum stepper motor movement, we were able to look at the motor specs. Our NEMA 17 motors have a 200 steps per revolution, multiplying that by the pitch of our ball screw that we are using, we were able to get a step of 0.025 millimeters.
For the liquid handling subsystem, we have 2 different pipettes. The first of which is Opentron's P1000 Generation 2. Now, my favorite reason for why we chose this one is that it simply works. Labs around the world use these pipettes, and for various reasons. The automatic pipetting, which helps ensure no contamination occurs within the individual wells and test tubes. It uses a tip ejector and disposable tips. It has one of the largest, if not the largest, volume range I could find in the market for an automatic pipette. boasting 100 milliliters to 1,000 milliliters for the aliquid volume. Its dispensing speed meets the required customer need, coming in at 274.7 microliters per second. With the accuracy for the smaller end, it's plus or minus 2 microliters to plus or minus 7 microliters for the higher 1,000 volume range. Following that same logic, the precision is plus or minus 1 microliters to plus or minus 1.5 microliters. Another huge reason why we chose the Opentron P1000 Generation 2 is because it's open source. So I had a lot of questions about this, so I scheduled a meeting with Opentron, and they set one up with me with one of their representatives. And I asked if I could just buy the pipette itself and attach it to our own gantry system, because they have their own OT2, their own liquid handling robot where this pipette's attached to. They said, yes, it's open source. You just have to connect some data. Bada bing, bada boom, it's in. Nice and simple. But now that was out of the way, I did have another question. Would it create any aerosols? I'm going to be honest. In the beginning of the semester, I didn't think aerosols were that important. I was more worried about the volume range or the accuracy and so on and so forth. Then, just to be sure, I scheduled a meeting with one of the customers, and I asked them, how important is the aerosols? Be honest with me. And I heard horror stories. And then coincidentally, a few weeks later, a friend of mine who works in a lab had to be evacuated from a lab because of the aerosols contamination. So I was vigilant in calculating the Reynolds number for the different pipettes. For the Opentrons, I used LB broth, which is the most popular media for growing bacteria. Putting in the dynamic viscosity and density and the diameter, I discovered that the Reynolds number was 636.46, which is luckily less than 2,300. Thus, the flow was laminar and no aerosols in the Vitatron so far. Next is the scaled up Opentron. Welcome to level 2. So because Opentron is open source, they have a GitHub with all the code on how the pipettes move and a bunch of other stuff, but mostly the code. With that, we can connect it to our own scaled up version of the pipette. The reason why we decided to have a scaled up instead of just having one pipette that does the entire volume range, which on the customer needs statement was 5 microliters to 20,000 microliters. That range is it's too large. It doesn't matter what funds we had, we wouldn't have been able to meet that volume, or if we could, the accuracy and precision would just not be satisfactory. So we had 2 pipettes, this one handling from 1,000 to 10,000 microliters. The dispensing speed is maintained at 274.7 microliters per second, while the accuracy, because it is a larger volume range, is not as good as the previous one. It still is satisfactory, coming in at plus or minus 5 microliters to plus or minus 12.5 microliters, and the precision is plus or minus 1.5 microliters to plus or minus 5 microliters. And of course, I had to calculate the Reynolds number again. This time, the diameter was a little larger, but thankfully, it came out as 1,702.54, which is still less than 2,300. Thus, flow is laminar and no aerosols in the Vitatron. On the right, we have a graphic just showing how the 2 different pipettes would be mounted for the up and down motion on the gantry system. We use this triangular prism that helps.
Driven by our design model on compactness and modularity, Vitatron gantry system drives another subassembly, the optical measuring one. Current microplate readers offer high throughput screening of cell cultures. However, they are limited to specific excitation lights and specific well plate diameters. Vitatron optical measuring system instead is designed to continuously obtain of the optical density and Fi fluorescence intensity readings of the cell cultures at any time, guaranteeing the user the possibility to autonomously configure the excitation light's wavelength and its beam diameter. Moreover, our system is synergized with our automated pipetting system and our centrifugation system to mesh together to offer our customer our all-in-one experience. As you can see from the pictures in the slide, we broke down the ODFI systems into main components. The exciting light source is shown in the top picture, and it is attached to the gantry system by a aluminum CNC machine bracket, which offers a movement speed of 275 millimeters per second, plus or minus 0.08 millimeters in movement precision. What makes Vidatrons unique, though, is our wavelength selector. Our wavelength selector can generate any exciting light at any configurable wavelength in order to autonomously perform a variety of screenings without human intervention. The beam diameter is then regulated by adjusting the distance between a biconcave lens and a collimator in order to fully irradiate welds of different sizes. Once the light hits the cell culture, it gets absorbed, and the emissive light gets filtered by a fluorescence filter wheel located underneath the weld plate. In our design, as you can see in the bottom picture, we have a fluorescence filter wheel which hosts 3 emissions filters that are used for standard fluorescence intensity measurements. However, the customer can integrate up to 6 filter lenses. And if you would like to have a slot for optical density measurement, you would just have to leave one open. The light that gets filtered then goes through a transmitting grating, which then diffracts into a linear CCD sensor located underneath the wheel. The CCD sensor reads the light input generated by the emissive light, and then it converts it to an electrical signal using an ADC, analog digital converter. The data is then transmitted to our user interface using a micro USB connector plugged in the PCB of the CCD sensor. Both the filter wheel and the sensor are mounted on a 3D printed platform. We have chosen a 3D printed material for our platform to reduce our cost. As you may know, products in the optics market are quite expensive, and our subsystem has the majority of the components being off-the-shelf parts. Therefore, we reduce the cost by 3D printing our platforms and our housing for the wavelength selector, which also allows us to have a lower weight of both components. Reason why we have chosen a belt-driven actuator to move around the fluorescence filter wheel and the sensor underneath the weld plate to obtain measurements of individual welds. Moving on, the excitation light's wavelength selection is being performed using the diffraction equation and by obtaining a relationship between the distances between the exit slit and the diffraction grating itself. As you can see on the top, on the left picture, our exciting light is generated by a white LED source, which is then diffracted by the diffraction gradient oriented at 45 degrees angle to the horizontal axis, generating a full visible light spectrum. We can select the wavelength of the light source by simply adjusting the vertical distance between the exit slit and the diffraction grating using a Z dovetail stage, which has a travel stroke of 5 millimeters with plus or minus 0.01 millimeters. In order to determine the distances required for our desired wavelength, using the geometry shown in the top right picture, we have determined the horizontal distance between the exit slit and the diffraction grating for a specific wavelength at one specific height. Once we have done that and we have determined that the horizontal distance was 7.53 millimeters, we have then related the height to the fixed distances at the different wavelengths. And as you can see on the bottom right, we obtain a summary table of all the required distances between the slit and the grating itself. Furthermore, we have developed and designed a beam expander using a biconcave lens and a collimator in order to fully irradiate welds of different sizes. Once we have chosen both lenses, we have determined the magnification of the beam expander to be 5.08. We have then determined the divergence angle to be 13.48, and using the same trigonometry, we have established a relationship between the distance between the lenses and the desired well diameter. As you can see on the bottom right, we have the summary of standard well plates with their relative diameter and the distance required between the lenses for it to fully irradiate the well. You're probably wondering, would the light intensity generated by this system, would it be enough to be even read by the sensor, or would it be too powerful to kill the cells itself? Analytically, we cannot prove that because light intensity follows an inverse square law. Therefore, we would need calibration, which would happen in the prototyping stage of the design process. Therefore, once we can identify the intensity of the light source at one specific distance, we can calibrate it so that we can determine the intensity at one other distance. Therefore, we have assigned the technical readiness level 2 for that system.
The agitator works synergistically with the ODFI system. As you can see, there's a cutout in the linear platform, and there's also a cutout in the orbital platform, which is covered in this picture. So the ODFI system, the top ODFI system and the bottom ODFI system can interact with each other. Linear motion is created by a single stepper motor that is attached to an offset rotational shaft that has a track roller. This track roller moves within a guide rail that sits below the linear platform in order to create the linear motion, along with two sets of a carriage and guide rail on the other side, which help constrain motion linearly, as well as provide stability for the agitator. The linear motion has a 50 millimeter stroke and a 50 to 300 RPM speed range. Orbital motion is created on the top platform. This is also powered by a single stepper motor, which is attached to an offset rotational shaft. On the other side, there are two offset rotational shafts, both supported by bearings in order to provide stability and allow for smooth motion. So our orbital platform has a universal seating, which allows us to fit either any well plate or a 3D printed Falcon tube rack. This Falcon tube rack can fit 5 50 milliliter Falcon tubes and 6 15 milliliter Falcon tubes. So our universal seating has a rubber trim on all four sides to account for any thermal expansion of the well plates and Falcon tube racks. This assures that the well plates and Falcon tube racks will not be damaged in any increase in temperature. Our agitator received a technical readiness level of 3. As you can see in the middle pictures, the top picture shows the linear motion and the bottom picture shows the orbital motion. A combination of the linear and orbital motions will allow us to create double orbital motion. On the far right, we have an exploded view that shows in better detail our track roller and guide rail, as well as our carriages on their guide rails. So since the motors will be running pretty constantly throughout the life, or the expected 10-year life of our bioreactor, we had to calculate whether the motors would last for that amount of time. To do this, we used the weight that each of the motors will be moving, as well as half of the linear stroke and the orbital radius of our agitator. Combining these, we were able to find the torque needed for each of our motions. Along with these, we used a speed ratio and a torque ratio using manufacturer provided specs on their that they used for their lifetime calculation, and this allowed us to convert their lifetime number to our lifetime number using our operating RPM and our operating torque. We also used a load type factor which accounts for any change in motion of the agitator. So for double orbital, we have a load type factor of 2 because in every cycle, the orbital motor will have to reverse in order to create the double orbital pattern. Our linear motor had a load type factor of 1 since it will be moving in the same direction the whole time. Using all these variables, we were able to find a 13.2 year lifetime of our orbital motor, as well as a 9.59 year lifetime of our linear motor. So while the linear motor is below the expected 10-year life of our bioreactor, this is only for if the agitator will be working 24/7 constantly for those 9.59 years. So our agitator will last over the 10 years if it is not moving constantly. Furthermore, our agitator uses removable motors that are only screwed in through 4 screws, so the motors are easily replaceable.
And so to further ensure the longevity of our agitator, we also decided to analyze components of it that would be constantly experiencing stress. So that would be the rail mounts, the linear motor mount, and the linear platform. So for the linear platform, you can see it in the picture in the bottom left of this slide, and you can see how it has a cutout in the middle for ODFI measurements, and you can see how it's asymmetrical. So it's asymmetrical because on the left side, it supports the orbital motor, while on the right side, it only supports 2 ball bearings. This difference in what they support also causes an imbalance of forces that the linear platform experiences. So due to the imbalance of forces and the unique geometry of this linear platform, we decided to evaluate it through a finite element stress analysis in SolidWorks just to ensure that there are no stress concentrations due to our design choices. So as you can see, it's mostly dark to light blue, which would indicate 0.5 megapascals being experienced. And since this is made out of 1045 steel, whose yield strength is 310 megapascals and whose ultimate strength is 565 megapascals, we can safely conclude that there are no concerning stress concentrations due to our design choices of this. And our factors of safety for both strengths are also listed there. So with the motor mounts, we were concerned about the moments that they would be experiencing due to each motion. So for the rail mounts, the motion that they would have the hardest time dealing with would be the moment coming from the orbital motion. And for the linear motor mount, it would have the hardest time dealing with the linear motions moment. And so considering these things, we use the weight from the previous slide for our torque, as well as a second moment of area calculated as a hollow rectangular shape that you can see in the center picture there. So through these things, we calculated the bending stress that each motor mount would be experiencing in their worst case scenarios. Using that value, we can also plug it in to find the number of cycles it would take for the motor mount to fail. So we would use that bending stress value, a modified endurance limit, fatigue strength factor, as well as the material's ultimate strength, which is also 1045 steel. So it would be the same ultimate strength used in the previous analysis. So the definition of infinite life for steel is about 10 to the 6 cycles. And for us, the rail mount would fail at 10 to the 37 cycles, and the linear motor mount would fail around 10 to the 28th. So we can safely conclude that both motor mounts would achieve infinite life. And so we determined our speed range based off of our orbital diameter, our linear stroke, and other current shakers that are on the market. But with this speed range, we still needed to ensure that there would be no spilling over the sides of the well plates or the Falcon tubes, because we definitely do not want any contamination to happen in the Vitatron. So to ensure this, we did a hydrostatics analysis using a pressure variation equation. But before doing so, we had to do a couple of assumptions. So the first main assumption would be that 2D linear motion on the well plates would be what causes the biggest liquid sloshing height. The second assumption would be that the fluid that fills the well, which is the cell culture, would fill it up about 70%. And then the third assumption would be that there is no pressure differences in this system. So with those assumptions in mind, we can figure out the change in y, or the change in liquid sloshing height, based off of the acceleration in the x and y axis, as well as the change in distance in the x axis. So our agitator does not have any acceleration in the y axis, but it does in the x. And we did this we figured out the acceleration in the x axis just based off of what we would think the biggest difference in velocity would be in our agitator. So that would be from about the middle of the linear stroke back right to its end, where it's just about to change direction. So in the table there, you can see that we did this analysis for both a 6-well well plate and a 384-well well plate. So while there's spillage in the 6-well well plate, the 384-well well plate does not experience it, but it is pretty close. And this is also based off of our assumption that it is only filled, that the cell culture only fills up 70% of the well. So in order to be safe, we would still apply a clear adhesive film on the well plates before they are inserted into the Vitatron that is clear once again, so that ODFI measurements can be taken. And they also are pierceable and have pre-cut X's in the middle of them, so that the liquid handling pipette can add or subtract liquid as needed. And so the price of this would be $120 for that film.
And then going down to the budget pizza, we have this. The 3 subsystems we allocated the most funds to were the liquid handling, the ODFI measurements, and the heating and cooling. Our total prototype cost comes in at $9,829. And then when adding the manufacturing and labor, it comes into a total of $10,697 for the Vitatron. Now, ever since our baby gator days here at the University of Florida, we've been told the same old mantra over and over again from our professors. My favorite version of this is one from Jonathan Brooks. Keep it simple, stupid. And we wanted to do that. We wanted to meet the customer needs, the complex needs, with simple solutions. It's what sharpened our marketability, maintained a compact form, all-in-one modular design. And as you can see, we reverse engineered various components from the market to all work seamlessly. It amplified our synergy and gave us that competitive edge.
For example, our ODFI system is inspired from a spectrophotometer. However, our system allows configurable and customizable wavelength for different configuration of experiments without human intervention. And it also synergizes with the liquid handling.
Liquid handling, we took our inspiration from various other companies such as that make 3D printers, and also from Opentron as well. We based our design from those because they have proven components that are shown to last. They are components that are easily obtained because of their low cost, and they're components that are easily able to meet our customer requirements, and they're components that are easily synergized to work with other components because of our use of the Opentron syringe, and also because of our gantry system working well in tandem with it.
Our heating and cooling system was originally inspired by the way a CPU fan is cooled or other incubators in the past. However, the normal water jacket system has high costs in manufacturing as well as material. So in order to make our system more effective and keep the efficiency, we changed it to have the heatsink in there as well as the electric heater.
For the gas control subsystem, we drew inspiration from the Harris-Cell microbioreactor and their use of a HEPA filter.
Our agitator uses a Scotch yoke inspired mechanism with inflection points at the midpoint of the linear stroke in order to allow for smooth motion.
And the competitive edge in the housing lies in it being modeled after a refrigerator's composition for highest environment retention efficiency, of course, with special attention to the materials to meet customer needs, such as non-reactive, non-porous, and non-corrosive properties. We're offering you this compact, streamlined, modular bioreactor design for all your autonomous incubating needs.
Questions?
Phew. Okay. I was about to count down. Good. You guys got it in just in the right amount of time. Perfect. let's open the floor to our panelists.
I'm gonna jump the gun here first. Ahead of Tom, because I know exactly what he's going to go into. And I wanted to ask this question before he got there. So when you guys did your shaker, you mentioned that, and it was the first time I heard you guys call it a specific alloy, you mentioned that it was 1045 steel. Why'd you go with 1045 steel?
So we wanted to go with 1045 steel because our main worry with the agitator and its parts, specifically like the linear platform, was its lifetime, just because it would be experiencing several different stresses from different areas, such as like the imbalance of forces, and things like the pushing and pulling of the guide rail that's on top of it. So we wanted to go with the medium carbon steel rather than a high carbon or anything like that, just so it has the kind of like best of both worlds in terms of hardness and strength, while not going too high on cost.
How is a medium carbon steel going to manage in a humid environment or when being sprayed down with bleach to clean it?
Being sprayed down with bleach. Oh, do you mean for the just like general cleaning of the bioreactor?
I mean, yeah, somebody's going to spray bleach in there to clean it from time to time. Probably, it's one of the most common cleaning things in a bio clean room. So just asking, 1045 as an alloy, dealing with bleach from one side and also dealing with the inside of the incubator being a humid environment. How is 1045 going to manage in that type of an environment?
That's a really good question that I hadn't fully considered. I'm sure there could be some type of treatment that we could add to it that would add to our manufacturing costs to make it more resistant to things like that. But that is not something that I have a specific calculation for at the time. But thank you for that. That's a good question.
So while we're talking about the shaking system, I do appreciate the thought you put into fatigue life, because that is an important consideration on something that is designed to vibrate. On kind of a similar note, I noticed that your supports for that were sort of very tall hat brackets, and I'm wondering, I didn't see any discussion of natural frequencies that might be excited by your shaking system, but those in particular seem like they might have a fairly low resonance and potentially be excited by the shaking.
Yes, so that is also a good question. That was something that we were also considering. A previous design iteration of ours had just 2 motor mounts that were faced the same orientation, which would, and we had changed that to our current orientation now in order to kind of dampen the frequencies that it might experience. But we do still need to have we still need to do the explicit vibrations analysis on that. I was definitely planning to include that in the FER report. And if you would like to have that explicit number, I can also send that to you later on.
Okay, and I would suggest that that's not the only system in your Vitigator, or I apologize on the name, that could potentially have dynamic effects. Your little fluid dispensing gantries seem like a big long cantilever, which are pretty poor for having high natural frequencies. So I would imagine that something like that could potentially be excited as well. So check that as well.
Okay, yeah, thank you for bringing that one up as well.
The thing that I thought Dr. Nemi was going to point out when he said Tom's going to hit on this is I saw a FEM of the plate on the shaker table.
Mm-hmm.
Could you flip back to that? Could you flip the slides back to that real quick? There we go. So to me, this looks like 2 beams with a couple of point loads on it. And I would suggest that and I'm glad that Zachariah mentioned the KISS principle. I would suggest that applies here as well. That this is way overkill, and if I had to guess just from previous teams, I can't tell necessarily from looking here, but if I had to guess, I would guess this is a 3D TET mesh of a very flat plate, which if it is, that's way the wrong way to do it. Even if it's a 2D mesh is still overkill. Just do a beam analysis on something like this.
Okay.
Yeah.
So it would be like 2 beam analyses on like each side is what you're saying.
Yeah, because that's exactly how this structure is going to behave.
Okay.
A couple other things. You showed a film cover on this. Is that going to interfere with gas transfer? You've got requirements for the atmosphere in your system. Is that atmosphere going to be able to get through to your little beasties in these wells?
So yeah, the way this one would work was that they would have pre-cut X's into them. So then that would help with the gas permeability. And the one that we chose is specifically for long-term use of cells in tandem with robotics and automation. So that would be not a big concern, but I can also double check the material that it's made of just to make sure it's as gas permeable as it should be for this application.
Okay, I would recommend coordinating that with the customer. Another team kind of came up with a similar idea, and it just kind of raises the thought in my mind that the folks in the lab seem, at least from all the earlier presentation that I'd seen, seem like they were thinking this is just going to be open to the environment, and there wasn't going to be any sort of barrier, so they don't have any requirement for gas permeability because they're not anticipating anything for it to permeate through. So I would run that by them and see what they're expecting, and if this system, which I said before, and I'll say for your team as well, is a very clever system for preventing the kind of splashing and aerosolizing that could be a problem. So I definitely appreciate it as a solution, but make sure that the customer is on board with that.
Yeah, that's definitely something we should talk about with them, since this is an additional solution that they probably hadn't considered customer needs for at the time.
So I guess we still got time, and I'll hop in and ask another question here. So your costs, about a quarter of your total costs came down to liquid handling. I know exactly why. It's because you're buying an OTS pipette, and then you designed your own other pipette for the other size. Why not just not buy the OTS one and design your own for both sizes?
I think that would be too risky because I want to get so the way I thought of it was kind of like the reverse engineering report we had in the beginning of the semester, where we had to buy the fire piston to get all the exact little nuances and measurements. Because like on the labeling, it would say aluminum alloy, but we don't know what type exactly. With the Opentron pipette, they give us a lot of information, but not every little single detail, which is why it's a technical readiness level of 2 instead of 3, because there's still more I want to dive in deeper on to better understand it. And then also the reason why liquid handling is pretty chunky is because we also use ball screws instead of lead screws, because we want to just have that extra insurance for avoiding backdrive problems in the gantry system. So ball screws are a little more expensive as well, and that's why the cost went up.
So then on that point, is it necessary to be that accurate?
So yeah, that's a good point. I think it is, because there's individual wells that have a really small diameter, and I wanted to be sure all of it could be met and needed. Additionally, the pipettes had to go and pick up the disposable tips. So I think the accuracy is within reason and justifies the cost.
Okay.
Okay, thank you.
Just to add on, since we're talking about cost, while the agitator is a smaller slice of the pizza, another way that we could reduce cost is like what was it? You saw that the fatigue life for the motor mounts are very, very high, even when comparing it to the definition of infinite life. So we could switch that out to a thinner steel or a less expensive one that would still meet the infinite life requirement.
Okay. Any other questions from the panel? We ended up starting about 5 minutes late. So even though the session is meant to end at 2:30, I'm happy to continue on for about 5 more minutes if additional questions would like to be asked.
Yeah, so the heating and cooling analysis that you guys did, you said that you were within range to achieve your temperatures within 15 minutes. Was that it seemed like that was the temperature of the atmosphere, not the temperature of the media in the wells or in the tubes. Is that correct?
Yeah, so we had looked at having like a water jet system around the weld plate specifically, but from a control standpoint, a lot of controls work by overshooting, and if you overshoot directly by where the weld plate, like where the weld plates are, you could potentially, I don't know, kill the samples depending on, you know, the temperature range that they're expected to go. So if you have it in the environment and we have 2 thermocouples on both sides of the system, we ensure that there's no more than a 4-degree gradient from where the heater or chiller is to the other wall. Therefore, whatever temperature that the weld plate is experiencing is within that comfortable range, and we give ourselves like a buffer to not accidentally kill the cell cultures.
Okay. What specifically is the customer's requirement, and how much, you know, if you've got your the environment in your chamber reaches 70 degrees C, how much longer is it going to take for the media to hit a somewhat uniform 70 degrees?
It shouldn't. So the weld plates, can you scroll to a different picture, Zach, of the whole environment? Okay, thank you. So when we did the calculations at first, we did the calculations with the gases specified by the customer. So it wouldn't be like room temperature or like, you know, the gases in your typical room. It would be the gases specifically in the environment. So that's what like how long or how much energy it would take to heat those and cool those. And like that was the customer requirement, like getting the chamber to be those specific temperatures and not necessarily like the cell cultures themselves.
Okay. Granted, I'm not the customer. I didn't write the requirement, and I'm not in the lab and don't have a perfect understanding of how this works. But if I were interested in you know, growing cell cultures, I'd be interested in the temperature of the cell cultures, not necessarily the temperature of the environment. So that's kind of why I'm thinking that might be a misinterpretation of what the requirement actually is.
Perhaps we have to like look into the different cell cultures that they will be using. From my understanding, I didn't think we were given specifically all the different cell cultures that they were going to be using. So obviously the values would change based on their densities and properties as well.
I would guess it's probably pretty close to water, regardless of what's in there.
That's a good point. I hadn't thought about it.
But yeah, I mean, the main point is communication with the customer, and that tends to be key when requirements are somewhat vaguely written. And I remember taking a look at the requirements, I believe last semester, and thinking, yeah, some of these are you know, sort of hand wavy. You know, we want it to be able to do this, but they don't really tell you what this is or what the parameters of doing that are. So I think there's a lot to be gained in, you know, kind of sitting down and having those discussions about, you know, how you interpret the requirement and make sure it meets their needs. Because customers are notoriously bad at writing requirements.
All right, so we might have time for maybe 1 or 2 more questions. And Zach, am I authorized to open up the floor to non-panelists if we've got peers that want to ask questions?
Absolutely.
Okay. Adam's got a question about ODFI.
Yeah, so if you're using the films that you described to cover the well plates, I know the picture you showed, it was like an opaque material. Is it actually clear? Because I'm wondering, depending on how you measure your ODFI, that could cause like some occlusion in your measurement, right? Is it actually clear?
Yeah.
Oh, here.
Sorry,
Do you want to talk about the ODFI, or do you want me to talk about the film first?
You can talk about the film.
Okay, yeah. So for the film, yeah, it is clear. In the data sheet, it specifically says that it is the optical clarity of it is enough for ODFI measurements.
Just wanted to mention that since the ODFI is going to be calibrated during the prototyping stage of the design process, it's going to be calibrated to the transparency of the film itself.
Speaking of, you guys probably put more detail into the optical measurements than any of the other teams that I've seen. I noticed that you guys are measuring through the vertical length of the samples. How sensitive to the depth and potential, curvature at the bottom of your well plates and test tubes are you going to be?
That depends on the density of the fluid itself, and there's a Beer's law that will regulate the actual absorbance based on the distance of the light traveled within the sample.
Well, I guess the question is more, how is that going to affect the accuracy of the measurements that you're making? If if you've got a little more depth in the well plate than you think you do, or if you're measuring through a curved surface, how's that going to impact your measurement?
Yeah, since it is programmable, and we still cannot determine the actual light intensity, and therefore its accuracy with it. Once you do calibrate it, you can actually program the user interface such that you can select what type of well plate you're loading in the machine, and therefore what type of media it's being inserted. And by analyzing the data and inputting it into the program, the machine itself will be able to render and get the to be tiered so that the accuracy of the measurement will not be affected by it. If that helps.
Yeah, I think so. I guess I'd want to see, sort of that would be one of the proofs of concept that I'd be interested in when you get to the testing phases. How accurately, given the precision at which you've got a volume of fluid in there, how that impacts the measurement.
Yeah, unfortunately, I can't. We could not analytically solve for any of the optics analysis that would pertain to the power and the light distribution of our optical system. However, they were taking into account, and since we were aware that a lot of losses were given by the lenses themselves, the well plate, the film, the media, we were trying to reduce all the other losses that we could control, such as the choosing a CCD sensor to reduce the thermal noise in the data acquisition, and the same as positioning the sensor at one specific distance with the grating, such that the light itself will be fully captured within the sensor.
Okay.
Thanks for your question.
Okay, so on that note, I don't want to run too far over, because we would like to take a little break before we reconvene. So let me just one more time thank Group 4, Vitatron, for your presentation. When I saw splitting up Vita and Tron, I thought you were going to talk about Tron the movie.
The font is actually the same font, so we did pay homage.
Yeah, no, that's yeah, exactly what I was thinking.
And I
And-
also want to thank the sponsors, Northrop and Cummins, and you, Dr. Trom, and Dr. Nimi, and of course our amazing TA, Aaron, and my team. The team's awesome.
Yes, it is. There you go. Very good.
Thank you.
Okay, great. So thanks, guys, for sharing your design with us. And we'll wrap it up there. So let me hit the stop record button.